Alright, so this is part 2 of our capacitance videos. The first topic that we're going to be talking about in this video is the energy stored in a capacitor, and the second topic is about connecting multiple capacitors within a circuit, okay? And we'll look at both series and in parallel. So firstly, taking a look at energy. The energy that is stored in a capacitor is electrical potential energy, which we can denote as EP, okay, like we always do. When we connect a capacitor into a circuit, okay, like so, energy is required in order to push charge onto the plates, right? And we know this energy is provided by the EMF of the power supply, and so what this results in is charge being accumulated onto this plate and a lack of charge being accumulated on this other plate. And so we have our formula from level 2, which says our work done is equal to the voltage times the charge. And if you don't remember this formula, it took the form of E is equal to QV, okay? So we have our E, which is our energy, and that's our work done, obviously voltage, and then Q for charge, all right? And so what this equation says in words is that 1 joule of energy is required to move 1 coulomb of charge through a potential difference, which we can denote as PD, of 1 volt. Okay, so that is what this equation says in words, alright? And so as I said previously, this equation can be written as E is equal to QV, or in this case, we can replace our E with a W for work done, okay? And remember, this equation comes from the fact that voltage is the amount of energy per coulomb of charge, and so this is just a rearranged version of this equation. Okay, and so once we've gone through this process, once we've done work in order to push the charge onto the plates, we have a slight issue. The issue is that the work done to move charge onto the capacitor does not equal the energy stored in the capacitor. Okay, so the reason for this issue / conundrum is the fact that if we draw a parallel to what happens in mechanics, if we have little Timmy over here, okay, and Timmy has a box that's on the ground, okay, and so if we were to look at the work done required to lift this box 1 meter, let's say, okay, let's say it takes 1 Newton of force to lift the box 1 meter, then the work done is equal to the force times the distance, and therefore it's 1 times 1, and we get 1 joule of energy. And so that is the work done required to lift it up, but once it's up here, we know that that is going to be equal to EP is equal to mgh, okay? Because now it has gravitational potential energy, and this is force times height, which is 1 times 1, and that's equal to 1 joule. And as you can see, the work done in this case is equal to the energy stored in the box when it is lifted up, okay? However, what we're saying here is that the work done required to move charge onto the capacitor does not equal the charge that is stored in the capacitor, okay? So you see the slight issue that we have right here. So the reason, as you might have guessed, okay, so the reason is because energy is lost in this process of moving charge onto the plates, okay? And the reason for this energy loss is because as the charges flow onto the capacitor, this obviously results in a current being present, okay? This is pretty self-explanatory. If there is a flow of charge, that means there must be a current present because that is the definition of current, okay? And so we learnt from internal resistance that if there is a current present, current dissipates energy as it flows through the wire, okay? And so this is where our energy loss comes from, all right? And the rate in which we lose this energy is P is I squared R, okay? And so we can see this by looking at our graph that we saw in the last video, where we have our voltage here and our charge here. And we saw in the last video it's going to be a linear relationship, okay? And let's say we push this much charge onto the capacitor, okay? And so we're gonna have this much, like so. Let's call this Q1 and this V1, okay? And so the energy stored in the capacitor is the area under our QV graph, okay? And so this is now the energy stored in the capacitor, which we can denote as EP, okay? When V1 is across the capacitor and Q1 is stored in the capacitor. And so as you can see here, the area under the graph is a triangle, and we know the area of a triangle is equal to half base times height, okay? We have our base here of V1 and our height of Q1, and so we have half Q1 V1, okay? And as we denoted, the area is our energy stored, and so we have EP is equal to half QV, okay? And just a reminder, the 1 in Q1 and V1 is just an arbitrary charge and voltage value, okay? And so what you would probably see in your formula sheet is EP is equal to half QV, okay? And as we saw over here, our work done is equal to QV, okay? So our work is equal to QV. And so as you can see, only half of our energy that we inputted, which is our work, results in potential energy, okay? Another equation that might come in useful is we know that our capacitance is equal to the charge all over the voltage, okay? We saw that in the last video, all the way up here, okay? And so therefore we know that Q is equal to the capacitance times the voltage, and we can sub in this for this, and we get EP is equal to half CV times V, and so therefore our potential energy is equal to half CV squared, okay? And so if we don't know the charge stored onto capacitor, but we know the capacitance of that capacitor, and we also know the voltage across the capacitor, we can still find the energy stored in the capacitor. All right, and so that would be it for energy stored in a capacitor. Now, another thing we need to know is what happens when we connect multiple capacitors in a circuit, okay? And we also need to know the differences between when we connect them in parallel versus when we connect them in series. So first, looking at capacitors in parallel, all right? So if we were to have a section of a circuit right here, where we have a capacitor right over here, and another capacitor over here, okay? You can see that these are in parallel. We'll call the capacitance of this top capacitor C1, and the capacitance of this bottom capacitor C2, okay? And so the question that we want to ask is, what is the total capacitance of this section of the circuit, okay? And so what that is asking is, if we were to model these two capacitors in parallel as just one capacitor, what would the capacitance be of this capacitor, okay? And so what that is our total capacitance is our effective capacitance. And remember, our effective capacitance is just what I said previously. If we were to model these two capacitors that are in parallel as just one capacitor, what would the capacitance of that singular capacitor be, okay? And so our total capacitance, or our effective capacitance, is equal to C1 plus C2. So we merely just add the capacitance of the capacitors together. Now, if you want to know where these equations come from, it's one of the first videos that I made, and I think it's also on the scholarship playlist, so you can go check that out. But not gonna lie, when I made those videos, I wasn't very good at making videos, and so I'm going to go through it once more. So because these capacitors are in parallel, we know that the voltage across them is going to be equal, okay? And we can denote that as V, okay? We can also denote the charge on this top capacitor as Q1 and the charge on this bottom capacitor as Q2, okay? We know that C is equal to Q all over V, and so our total capacitance, or our effective capacitance, is equal to the total amount of charge all over the voltage, okay? And remember, the voltage across both of the capacitors are the exact same. Our total charge is going to be equal to Q1 plus Q2, okay? So the total amount of charge within the section of the circuit is just the sum of all the individual charges, okay? And so rearranging this formula, we get Q is equal to CV, okay? And so therefore our total charge is equal to C1V plus C2V, okay? And so therefore we can rearrange this equation now and get our total charge is equal to the total capacitance times the voltage. And so therefore we get CTV is equal to C1V plus C2V, all right? And now we can divide by V on both sides, and we cancel out the V, and we get CT is equal to C1 plus C2, okay? And so that is how this equation came about. All right, so that is what happens to capacitors in parallel. Capacitors in series, if we were to have a section of a series circuit, and we have two capacitors right here. Again, we can denote the capacitance of this capacitor as C1 and the capacitance of this capacitor as C2. The equation for this is 1 over CT. Remember, CT is our effective capacitance, meaning if we were to model these two capacitors as one capacitor, the effective capacitance is the capacitance of that singular capacitor. And so 1 over CT is equal to 1 over C1 plus 1 over C2, and that continues on if we have more capacitors. Now, where did this equation come from? Again, I go through it. It's one of my first videos that I made. However, like I said previously, I don't think that video is very good, but it's still up, so you can go check it out. But I'll go through it once again in this video as well. Because these capacitors are in series, each capacitor must have the same amount of charge on them, okay? And so each capacitor must have the same charge on it, which we can denote as Q, okay? The reason for this is because there's only one pathway for charge to flow. And so when charge flows onto here, what's going to happen is we're going to have an accumulation of positive charge over here, which is going to attract the negative charge from this side and push away the positive charge from this side. And what that's going to result in is some more positive charge being accumulated over here and negative charge being accumulated over here. And that chain reaction continues down the line, and because the charge has nowhere else to go, the charge on each plate must be equal, okay? And we also know from my video on what makes a series circuit that voltage is shared amongst components in series, and so we can denote the voltage across this capacitor as V1 and the voltage across this capacitor as V2. And so therefore the total voltage across this entire thing is equal to V1 plus V2, okay? We know that the effective capacitance, or the total capacitance, is equal to the total charge all over the total voltage, and therefore the total voltage is equal to the total amount of charge all over the effective capacitance, which is the total capacitance. Now remember, like I said previously, each capacitor has the same amount of charge, and so we can denote this as just Q rather than Q total. And we also know the voltage across the first capacitor, this one right here, is equal to the charge that is on that capacitor, which we denoted as Q, all over C1. And the same thing for the second capacitor, which is Q over C2. And so therefore we can simply plug this all into here, okay, like so. And we get Q all over CT is equal to Q all over C1 plus Q all over C2. And we can divide both sides by Q, and we get 1 over CT is equal to 1 over C1 plus 1 over C2. And if we had more capacitors, that would continue on and on and on. And as you can see, that is where we get this equation right here, okay? And that will be it for this video. See ya.